Hi, I'm Yaman from Xilinx Research Labs, and I want to talk to you briefly about our project called LogicNets. Deep neural networks, or DNNs, are very popular for tasks like image classification and object detection, but their use cases extend far beyond computer vision. In a wide array of domains ranging from large-scale, high-energy physics experiments like those at CERN, to line-rate packet inspection for intrusion detection in next-generation networks, researchers are looking to replace manual algorithmic implementations with DNNs. Certain applications like the ones exemplified here have to go through gigabits to terabits of data every second and make decisions based on it within microseconds. So we call them extreme throughput applications here. The question that motivates our work is, how do we mix DNNs into such extreme throughput applications and make sure they are running fast enough? To meet this challenge, we propose LogicNets. LogicNets is a co-design approach where we first define a specialized DNN topology for the task at hand. The topology is subject to design constraints, which we'll cover in a moment. Once we have decided on the topology, we train it with standard training techniques, and when we achieve the desired accuracy, we can directly convert the trained network into an FPGA circuit. This FPGA circuit is a fully parallelized implementation of the trained DNN, and owing to the special constraints we put on the topology, it has low logic depth and is able to achieve high clock rates and classification performance to meet the needs of extreme throughput applications. The foundation of our approach rests on the equivalence of quantized neurons and truth tables. Here's a 6-LUT, capable of implementing any function with 6 inputs and 1 output. Could we somehow expose what this LUT is capable of to a machine learning framework? In our method, we use artificial neurons with quantized inputs and outputs to do this. If we have an artificial neuron in PyTorch with a total input of 6 bits and an output of 1 bit, we can always convert it into a single 6-LUT by enumerating each possible input and observing the output to construct a truth table. Note that the artificial neuron can have floating point weights and complicated functions such as batch norm inside it. All that matters is the total number of input and output bits. We can extend this concept to larger neurons and truth tables, but the implementation cost is exponential and quickly becomes prohibitive. For instance, a single neuron with 4 times 3-bit inputs and a 3-bit output would require a much larger truth table built out of a few thousand 6-LUTs for the FPGA implementation. And if we went to larger neurons, the cost would be even larger. We want to avoid an explosion in the number of LUTs. And to achieve this in LogicNets, we co-designed the DNN topology and imposed constraints on the fan-in. We use 2 key methods to design topologies with low fan-in. Let's examine how this works for a 3-layer topology. The first method is to ensure that the network is highly sparse, such that each neuron connects only to gamma previous neurons. The second is to use low bit activation quantization, such that each neuron produces a beta bit activation. For LogicNets topology design, we constrained beta times gamma to be less than or equal to 15 to keep the LUT cost reasonable. We have implemented a prototype LogicNets flow in PyTorch, where we start by defining the DNN topology and training it on the target dataset. Afterwards, we generate truth tables for each neuron, which we express in Verilog, and synthesize the resulting netlists in Vivado. We evaluated our approach on 2 tasks that are part of extreme throughput applications. These are the jet substructure classification task, targeting the L1 Trigal algorithms in CERN, using the HLS4ML JSC dataset, and the network intrusion detection task, where we try to classify malicious packets using the UNSW NB15 dataset. These 2 tables present some highlights from our experimental results on the 2 tasks, with a variety of network sizes and configurations, and I want to briefly point out a few things. First of all, we can see that the reported Fmax is quite high across the board. In some cases, it's actually faster than what the global clock network on this FPGA can support. These are fully unrolled designs with an initiation interval of 1, so we would be able to achieve throughput in the hundreds of millions of samples per second, with latencies less than 20 nanoseconds to meet the needs of extreme throughput applications. This is all made possible by restricting the fan-in of the DNN topologies, as you can see in the table, which yields simple circuits with low logic depth. We also observe that by adding more layers and increasing the fan-in, we can obtain DNNs with increased accuracy, although this comes at the cost of more resources. There is a broad design space of LogicNets topologies that can be explored, taking accuracy and resource budget constraints into account. All in all, we believe LogicNets is a meaningful step towards being able to mix DNNs into extreme throughput applications. Thank you for listening.